Hi guys, I'm Łukasz, lead Gen AI engineer. In last two videos, we look how to optimize speed of Qwen, how to deploy it locally with LLaVA CCP vLLM, and get as much speed as possible. In this video, we'll look how to fit, even with minimal maximum model length, videos of any length, and how to compute them as fast as possible with minimal resources, with using everything possible to speed it up. Exactly like this, guys, we can see that the same movie is now computed in just 12 seconds. And just quick shoutouts. Most of these techniques that I find, I was also looking at other solution. So there is something like build search and summarization VSS agent with NVIDIA. So here you can basically test and launch agent to ask questions about video, what happens. Currently it's not working, but yeah, it is what it is. So the code is here. You can check it out, video search and summarization. And also for the models, why I choose specific models. There is really nice block here when you can check the performance on the models on different benchmarks. And as you can see, for example, the 9B and 4B have really close score for the benchmarks. On 2B, we have biggest jump. And here you can read about the architectures. And here, for example, we can see different benchmarks with video. And as we can see, these models perform extremely well. And basically looking at all the video parameters and so on, the 4 billion models perform really well for its size compared to others. As we see, the gains are not as significant. I mean, significant depending on the scale and so on. So basically here you can choose the right model that you want to use. So for OCR 2B, for lowest latency 4B, balance, and then no compromises 27B. I will use 4B billion parameters. And this is the Docker. All the setup will be at the end of the video. But as you can see, we'll start with two number of sequence. This is parallel sequence, and then 10,000 batch tokens and 10,000 max model length. And all of these parameters, how they work, and others that we will also touch will be explained now. Let's break down how VLM actually manages GPU memory under their hood. There are three key parameters that control everything. Max model length, in this case 16k 1000 tokens. It's per request context sig. The maximum number of batch tokens 12k, so per iteration token budget in a batch. And then maximum number of sequences, which in this case is 4. It's parallel sequence slots, so how many requests we can send to one scheduled batch in the same time. So why 30,000 token can fail and how much chunking can save the day? Let's dive in. First, the KV cage. During inference, every single token in a sequence stores two vectors, a key vector and a value vector. This lives in the GPU memory. As the sequence grows, say from 10 to 100 to 1000 tokens, the KV cage grows linearly. Each new token adds another key value pair that has to stay in GPU memory for the rest of that sequence lifetime. So as we can see here, we are adding more KV cage and we are filling the memory. This happens in self-attention layer of the model, but we don't need to know exactly what is it. This is the core tension in LLM serving. GPU memory is finite, but KV cage keeps growing. Now let's look at the max model length, which is maximum prompt plus output tokens per request. So the request context composition is the prompt tokens, so what we type typically, plus first generated token, and then the generated tokens on the output. And this needs to be lower or equal to max model length. In our case, as we discussed, we have 16k of max model length. And now we'll look at the requests that have 10,000 tokens. A request of 10,000 tokens is well within the 16k token limit. The request is accepted. But watch what happens at 18,000 tokens. It blows right past the limit. The request is rejected immediately. This prevents any single request from consuming all the GPU memory and starving other requests. Now let's look at prefill phase and the decode phase. So in the prefill, we get all the prompt tokens at once. So this is our prompt, combine of multiple tokens, and this is a compute heavy. Why? Because all of this we compute in parallel, because we do a lot of matrix multiplications with the GPU, and this is where the time to first token comes from. So the first token will be here as a G1 when this gets computed. So now if I play it, we see the GPU compute get used and the memory bandwidth not so much. And the decode generates tokens one at a time autoregressively, and it's memory bound because for each step we need all the tokens that get computed here and all the prefill phase, so the prompt. Now let's play it. And we can see we computed G1, G2, G4, G3, and for G1 we needed all these tokens, then for G2 we needed G1 and all these tokens, and for G3 we needed G2, G1, and all of this. This is what autoregressive means. And this is where intern token latency comes from. So these two phases have completely different resource profiles, and that matters for the scheduling. Now the maximum number of batch tokens. This is the per scheduler step budget. It controls how many total tokens the scheduler can process in single iteration. Think of it as a throughput cap. If this is set to 12,000 tokens, then in one step the scheduler can batch together requests that total no more than 12,000 tokens. Let's see the animation. So here we get sequence A of 5,000 tokens, then sequence B 4,000, and then sequence C, which is 12,000. And then suddenly you get sequence D. So this will need to wait for the iteration in the scheduler because we achieve the maximum token budget. So this single request will exceed this budget and can be processed in one single step, which is exactly the failure case we'll see soon and why chunked prefill exists. Now let's explain maximum number of sequence and continuous batching. Maximum number of sequence sets how many sequence can run in parallel. Think of this as slots on the GPU. The key insight is continuous batching, but let's see how first static batching works. So we get 6 requests, and the first ones were request 1, 2, 3, 4, so all our slots in the sequence are filled. And then we also get request 5 and 6, but they need to wait for all of this to finish, because in static batching, we need to wait for the full sequence slots to finish. So as you guess, it's pretty slow. Now with continuous batching, as soon as sequence finishes, the slot is reused. So now let's see. We'll finish one of these requests. So now request 2 is done. So slot is freed immediately. And now the request 5 come into slot 2. So as we see in continuous batching, the slots are freed individually and new requests get filled immediately, so we don't waste the GPU cycles. So this dramatically improves throughput under the load. Now let's look at scheduler policy in VLM. As we can see, the default one is first come first serve ordering with preemption when GPU memory fills. So we have the queue of requests that we get. So request 1 arrive at 0 seconds, B in 1, C in 2 seconds. And now let's see what happens. So we fill the active GPU slots and we are computing request A, B, C at the same time. And here we can see the KV cache and GPU memory. So as we compute, the GPU memory gets gradually filled up and it becomes full. Now what happens when it gets full? As we use the first come first serve policy, one of these requests, so the last one that arrived, C at time of 2 seconds, will be preempted, so swapped to the CPU, and we stop using KV data so we can finish the first request. Now when it finishes, the slot 3, so request C, is resumed because we have a free GPU memory and so on. There is alternative policy, which is scheduler policy of priority. So if GPU memory is full, the lowest priority request gets preempted. So as we can see, we have the request 1, which have highest priority, request Y have 5 priority. So we preempted the request Z to finish request X first. Here is a real failure case. Imagine Qwen 3.5 vision processing a video. We have 18,000 visual tokens plus 12,000 text tokens, which give us over 30,000 tokens. First we check the max model length, and we set up 16,000. So it will exceed that and it will get rejected, which will give us error. Then we will check max number of batch tokens, which is 12,000, but we still try to put 30,000, which is too much, so it will also get rejected. So this is common failures that you get when you set up Docker or VLM. So you need to know how many tokens you will expect and how many tokens you can batch, and so on. And these parameters influence also the memory of the model. Now let's talk about chunk prefill, which is the V1 default version in vLLM. This allows decode priority scheduling plus chunked prefill. So now how it works. For example, the last request, we have 30,000 token requests. It will be split into 8 chunks. But here's the key. Decode requests always get priority. So the request D and E will be processed first, and in each iteration, the scheduler will first batch all the pending decode requests here, and then it will fill the rest with the prefill. So in this case, 10,000 token budget. And then we get another request on decodes, let's say again 2, and we'll fill another C4, 5, 6 to the slot to fill the 12,000 tokens. And then we'll get just the last C7 and C8. So by doing this, all 8 chunks get processed, and decodes process first each step, so it allows us better inter-token latency. This latency is basically the latency when we get the first token from prefill, and then we do decode, so we generate autoregressively token one by one. This measures this latency here, and then prefill fills remaining budget, so we have better GPU utilization. This allows us basically to control if we want better inter-token latency, which is related to decode, or time to first token, which is related to prefill, by setting up the maximum number of batch tokens. So this gives you 2 benefits: better inter-token latency because decodes are never blocked by prefills, and better GPU utilization because compute-bound prefill and memory-bound decode opts to share the same batch. You can tune this to smaller batch tokens, give better inter-token latency. Larger budgets will give better time to first token, and so on. Okay guys, so now that we already know what are these all parameters, I'll just say that as before, we try to turn off every possible caching for the sake of the tests. And as we can see, I updated the VLM image. So we have newer version, but we still have some errors here. So probably we lose some performance, but we need to work with what we have. And this is the last video, 2 minutes video that we use. So as you can see, I run it and we get error that we exceed number of tokens. So what you could say is, for example, we can change prompt. I added few ones here that we can test. So this one, for example, also failed. But now what we can do, if you watch the last video, then you know that we can decrease the number of height, and then voila, it works, and we get the tutorial working and so on. But we want to make it work on much longer video, like for example this one. So yeah, this is like really old video that I found that I should be able to use, but I only use it for demonstration purpose. I don't want to have any copyright issues or whatever, so we'll not play it, but as you can see, it's pretty long. So now if we run it, we use 160 and we'll see if we can compute it or not. In the meantime, we can see this was the error and we got error again. So we exceeded the maximum context length. So now what we can do? Well, as we can see, this video is pretty long, but what we can do is we can chunk it, meaning that we fit only 30 seconds of video and we will get the results out of it. And then, for example, we can get the video type. So in this case, I will try to maybe do chunking first on 200 seconds. So while it's computing, which will probably take some time, we can look into the few prompts. So for example, you can do search and indexing, basically of notable scenes and so on. So when you do chunking, you will compute 30 seconds of video, 200 seconds of video, will get the chunks. And each time you get the output, you basically free up the memory. And then when you get all the chunks, you can use the same even model to summarize what happens or to ask some questions with some semantic search or whatever you want. Here we, for example, have understanding and summarization, tagging, simple classifier, and so on. So one of the viewers asked, can we classify videos to specific categories? And yes, we can. So for example, here we see that we run it. It takes 34 seconds because we do chunking, and we get category movie, other, and so on. Which is maybe not smartest, but good enough for the test. And if we remember, we have, so let's remember this number, 34 seconds. We have something like maximum number of sequences. So now let's try to do 2 sequences at the same time. So this was 34 seconds, and let's see how long it takes. So I'm back with the results. As we remember, it takes us 34 seconds to get the results, but now we get 26. Why? Well, if we look into the terminal, we can see that we run 2 requests at the same time. So basically, we speed up a bit because we could fit 2 requests. And as you can see, sometimes we get the output and one request was waiting and so on. So this is basic speed up that we can do. But we need to think about something because this case is easy. Okay guys, now I use understanding summarization, also set up max tokens. So they are with, let's say, maximum capabilities of what we have here. And we are running the video with the same chunking strategy. Now we'll be back with the results. Okay guys, so as we can see, we get 400 seconds and we have here the chunks of video described. I checked, and for example here there is narrative about the parchment to enlistment during wartime in around 2 minutes. And as we can see, we have train and so on. I don't want to really go into video, but basically this is the enlistment. So as we can see, because we generated much more output tokens, it takes us a lot of time to get. But we still get it because if I click the chunking off and I run this type of prompt, this will fail. And as we can see, we exceed number of tokens and so on. So there are like caveats to this here, because if we can fit the full video, then we can get 1 results, and from what I tested, it's quicker, but we'll also see it soon. But also, when we do chunking, we need to think about balance and fine-grained and so on. Like fine-grained would be for analyzing quick scenes to get as much output tokens regarding the scene, what's happening as possible, so we don't lose any information and so on. And if you notice, there is second parameter, which is overlap. So let's say we analyze a scene and the scene have like here 30 seconds, yeah? But if we chunk, so we finish from 0 to 30 seconds, and there is some action at around 30 seconds, and this action, half of this action is visible in the first chunk, and then the other half in the second chunk, then we kind of lose information. So what we can do is we can add overlap. And overlap basically means that in the first chunk, actually we can run it to see first, and then I will explain. So I will now add 10 seconds of overlap, 200 seconds, same parameters, and I will just maybe do understanding and summarization because, yeah. Okay guys, I'm back. We do 200 segmentation and 10 seconds overlap. So now when we look, we have from 0 to 210, then from 190 to 410. So basically by defining segment overlap of 10 seconds, we have 20-second window between 2 chunks, or 10 seconds more in the first segment and 10 seconds before in the second segment. This way, we shouldn't lose information, but of course, there is more video to analyze, so the change in speed will be also happening. And in this case, we have 105 seconds to run. Now, let's see, and this gives us 32 chunks. Now, I will do 650, and I will come back to you guys when it finishes. And also, as you see, I'm missing here. I get another crash of full Linux, so I think I do too many things related to video, like recording, streaming, camera, and so on. So we'll see if it fixes it or not. Yeah, let's be back with the results. I'm back with the result. I actually needed to reduce overlap to 2 seconds because these 10 seconds actually go over my limit. But I just wanted to show you tendencies. So as we can see, we have 10 chunks and only 26 seconds. So increase the speed with the same resources, yeah, but we get much less output because we get 10 chunks. And also, as you can see, in this case, we get wrongly formatted JSON. Even though we tell the model that we want exactly this format, we get something else. So this is a good point for digression. So basically, if you make an app and you expect LLM to give you output in the JSON format and so on, sometimes you can get these issues depending on the size of the model. And it's not good practice to do it like this. Help you to define structured outputs and with automatical retries and so on with different providers. I use it with API, but there are probably something like this also for local, so on. We can see here Llama CCP, Python, and VLM. So they added open support since last time I used it. So this allows you to use Pydantic to define basically the schema of JSON and auto retry if it fails. So you guarantee that you always get the exact output that you want here Yeah, because if this fail and you send it to the app or something, then you have full crash everywhere. Yeah. Okay, guys, so for the benchmarking, we created specific prompt that analyze video chunk and produce exactly 4 sentences summarizing the main visible events, 6 bullet points listing important actions or scene changes, and then exactly 8 keywords describing the content. And then use only visible evidence, keyed output, concise and factual. So here we want to basically generate more tokens because you want to see the performance of the decode. So how much tokens are produced after prefill and preprocessing. So basically the answer to what the user asks. Why? Because if we ask only on one word, like I do it before for quick tests, then the decode is not really measured because we constantly get 2 output tokens, so we don't see big increase. We can like only measure prefill and preprocessing. So in this case, I wanted a bit longer output to measure this type of stuff. We set up max tokens to 10,000, completion to 9,500, thinking of, for sake of time. The video is 1 hour, 45 minutes because it's quite long. So we lowered the height for 128 because I don't see big difference, at least in the cases, and we could recognize what's happening in the video and so on. Maybe it's in training knowledge, we don't know. The target video FPS it's up to 1 and sampling also up to 1, 650, so we get 10 chunks and then overlap of 2 seconds to not lose the context of the video. And the output shape in this prompt stay controlled because there are differences in latency and true output that are more likely to come from the backend configuration. So we don't want the prompt drift. So this prompt was basically designed to make the benchmark fair for comparing concurrency, attention backends, and container image differences. So it is especially useful for measuring end-to-end behaviors such as average latency, time to first token, true output, and so on. And now to the benchmarks. So request per combo. So basically repetitions of the request that we sent. So in this case, 5 times we send this video. Then I don't do warm up here because I do it myself in single run before, but maybe for the sake of clarity, we do warm up. And then target video test. So the same as was there, but you can basically put multiple ones and then measure, for example, for your task, how much time it takes. It generates graphs here and JSON that I will show shortly. And then the chunk parallel requests. So how many parallel requests are sent? So like one is sequential, we send request for one chunk, another, and so on. In this second one, we send 2 chunks at the same time, and then wait between the benchmark combos. I set it to 2 seconds because I noticed that if I send them ultra fast, there's a bit influence on the benchmark, on the speed and so on, because the model kind of don't trust it and I really overuse my resources. So for the sake of benchmark to be viable, we put a bit of delay. This is option when you can feed the full video, because then you have it as basically the baseline of what if you are improving or not. But it's hard to compare because if you load full video, you get one output. If you do chunks, you get the amount of output as chunks, so typically more, so it takes more time. But in general, what I saw, if you can fill the full video, then it's faster. And then we will look into Docker quickly. So here we have Docker that we will use for tests. So as we can see, we have maximum number of sequence. So this defines the concurrency that we test. So we set it to 10, like here. The maximum number of sequence, then the maximum number of batch tokens, 10,000, 10,000 again. And then what we change is we do test with all the attention backends that I can support. So flash infer, flash attention, Triton. The flex attention give me basically error that it don't work, even though the engine said it worked. So yeah. And then I also try the optimization level 3. So this is aggressive optimization of vLLM. Typically you run it on 2, but I just was curious if this will influence the score. Yeah, we sent the processor cache budget to 0, no prefix caching, so it don't cache the same video that we run multiple times, but I think there is still possibility with all the things that engine do. And then here I tested the CUDA nightly image for 13 CUDA and then latest to see, because in the recommendations for this model, it's to use the newest CUDA nightly. So for especially Blackwell GPUs, so I do test of the stable one and pull new images to basically make everything viable. And now here is the status of the run. So all of these files will be in GitHub repo and so on. As we can see, when it was created, what's the name, the prompt, all the parameters that interest us, base URL, the requested concurrency, the weights, and then the records of each run. We have the combo key, the preprocess request, total, time to first token, output, chars, round tokens, total tokens, and so on. And this goes through all of the runs, and then we have aggregated ones at the end from the combo key. So as we can see, we have segmented, 10 requests, 10 segment workers. That's how I define it in the program, and all the counts with some other parameters, but we don't need to dive deep into it. Okay guys, so now we look into the graphs. So the first one, the average latency. As we can see, here are the 3 attention engines that we use. The flash attention is the default one for me. So this is what VLM choose if you don't specify it. So we can see we have 70.9. And the latency here was defined as computing the full video and then the average by the number of runs. So in our case, we have 5 times the video and so on when all the chunks return. And as we can see, flash infer was the slowest because it takes most of time because it's latency. And then Triton was the fastest. That's why I then choose to do aggressive optimization, which actually improved the speed a bit. But at this point, I think it could be statistical error, but basically what it defines is the optimization levels here. So for example, if you want to start VLM faster, but then it's not as performant, but maybe you need it for quick compute and close it, then you can choose no optimization, fast optimization, and then default one. So yeah, full and piecewise Q diagrams, which we can see in the output typically. So I choose the aggressive one. It could equal to -0.2, but may include additional time-consuming or experimental optimization in the future. Yeah. So I'm not sure if they actually use it at the end or not. Let's see. Okay, so it's the same. So I tested it, but this is basically the statistical error. And then this is the stable latest image, which actually have lower latency than the Qwen image, which was recommended. So yeah, maybe it catch up, but it's also around the error rate here. And then through output, so as we can see, the through output was nearly identical for these 3, but there is actually a few differences here. So this is still just 4 per second, but yeah, basically confirmed that Triton was the fastest one here. And then we compare the speed up. So as speed up, we define the speed to compute full requests when we have all the parallelism of the chunks, so maximum number of sequence defined. For example, if we run it sequentially, we do 1 chunk, then 1 chunk, and then 1 chunk. But in this case, it used all chunks that were specified. So if we do 10, we send 10 at the same time, and so on. So as we can see, the speed up was around 70% for flash attention, then 60 for flash infer, and then for Triton attention around 75.6. Here actually 78. Yeah, so this is for the aggressive optimization, which equals the same. So this run looks like this. And then, so time to first token and then outlier ratio, but outlier ratio is not visible here. So we'll look at it in the table. But basically this is time to first token for all the engines. So as we can see, Triton was fastest in the default setup. And here there was a bit difference, but they should perform the same. But of course there is like, if the GPU was hot, if there are not processes run on the computer and so on, I don't try to run anything, but there could be some slight influence. And then the stable one was actually slowest. And then this is something that was interesting for me. So this defined the percentage of the total time that we spent on preprocessing. So basically changing video height and all the parameters before we clean the video and send it. So as we can see on different engines, it takes different amount of time. So it takes like 42% here for flash attention, and then the request was 50. This should equal to 100, but there is also then delay added and so on. So that's why it's not exactly the same. And as we can see, the stable one have actually longest decode request compared to preprocessing. And then we have the average latency by concurrency. So as we can see, 1 is the slowest for all engines, and then it go lower. And actually here there is like big difference compared to other engines just on 8, which is kind of suspicious, and then it goes really low. So there could be something happening here, because as we can see, the tendency was that all the runs, actually not all of them, let's maybe zoom a bit. So most of the runs have the best run here, and then it was nearly the same. But here we can see that we get the Triton with stable VLM have like big outlier here, and then it goes down to the lowest value. Okay guys, so if you watched before my last videos, like for example, how to compare VLM, SGLang, TensorRT, LLM, and so on, you can check somewhere here. Basically how to run this, as always, you just activate the environment. If you don't have environment, you just do UV sync, and then you activate environment again because it got created. And then all you need to do is just do UV run and run the server. And then if you go on this address with control, you are in the same window as I have. And the important part, yeah, this is the Pi project. It will be in the repo. I also defined some extra stuff. Okay, guys, so that will be all. I will be curious to learn in comments what you use Qwen for, the visual capabilities or even the text, image, and so on. And also, if you were interested in this video, you can check the other videos when we benchmark vLLM, SGLang, and so on, when we learn about concurrency in text, in audio, and stuff like that. And also, I will re-upload the last video with correct speed because I saw there were a lot of comments regarding it because I screw up. So yeah, see you.